Assalamu alaikum. Ahlan bikum jami'a. Hello everybody. Today we'll start with the first lecture of G212, Advanced Structure for Special Geology students, second year Special Geology students. Okay. In the beginning, we have to give a small introduction about, a brief introduction about plate tectonics. Actually, we discussed this matter before in the first semester with you. That our planet is consisting of several layers. The most movable layers is crust. This is crust. The rigid material at the outer periphery of the Earth. المواد الصلبة اللي موجودة على سطح الكرة الأرضية هي الكراست. Crust is solid materials at the periphery or outer layer of our planet. Okay. فالكراست دي عبارة عن صفائح تكتونية، أو يبقى الكراست is divided into several plate tectonics. Each plate is divided by what's called plate boundary. Its plate is defined by from each boundary, or bounded from each side by what's called plate boundary. For example, if you consider Africa as one plate, so Africa is surrounded by what's called plate boundary. Actually, African continent is ended here in the middle of Atlantic Ocean, not at the coastal line of Africa, because this part of Africa is a continental part, and this abyssal part of Atlantic Ocean moving with the same direction of movement, almost at the same way towards east. So the boundary here, it's called mid-ocean ridge, which spread between Africa and South America. So the plate boundary, which spread between Africa and South America, is mid-Atlantic Ocean, the mid-Atlantic Ocean ridge. Okay, so the plate boundary, defining of plate boundary, plates is a part of continent and part of ocean together is plates. Some plate is only oceanic plates, like for example, if we see in Pacific Ocean, we can see some parts of Pacific Ocean is plates. Here, this part of Pacific Ocean is bounded by mid-ocean ridge here and mid-ocean ridge here, and a trench here, convergent plate boundary, and trench here and trench here. So this part of Pacific Ocean is plates. Almost of this plate is consisting of oceanic crust. So plate may be a continental crust, maybe oceanic crust, maybe mix of continent and ocean. فاهمين يا شباب؟ يعني تعريف البليت لازم تكون محددة بمجموعة من البليت باوندري على حدودها. مش لازم تكون البليت كونتيننت بس او اوشيانيك بس، ممكن تكون كونتيننت بس او اوشيانيك بس، او تكون ميكس من الاثنين كونتيننت اند اوشيانيك مع بعض. طيب احنا كنا اتكلمنا كده في افتراض ان يكون الاثنين دول كانوا one mass. We suppose that Africa and South America were one mass, and due to divergence تباعد بين South America وأفريقيا, oceanic crust, new oceanic crust developed in between the two masses. This is what's called extension tectonic regime. Extension tectonic regime have a lot of structural pattern which developed during the extensional process. In this course, we have to deal with the different structural pattern that developed due to extensional tectonics. So extension is not focusing along plate boundary only, but stress will move through all of the plates. So any weakness plane or any plane here in this plate will affected by extensional stresses. Okay, that's what we have to discuss in this course. So the first lecture is extensional regime. Extensional regime mean we apply extensional stress at plate boundary, okay, due to divergence of two plates. Extension stresses will be distributed over two plates, okay. The result of extension is what's called rift. The extension start with intracontinental rift, because if we suppose that Africa and South America was one mass, so the two masses diverged and moved away from each other, resulted in intracontinental rift in the initial stage. If we are looking here in this part, with each active rift today in our planets is East African rift. East African rift is defined by north-south fracture zone. This fracture zone, okay, resulted from moving of this part of Africa towards east and this part towards west. Some lakes was developed in these subsided parts of Africa, like Victoria Lake and Tanganyika Lake, Lake Nyassa, and so on, Lake Albert, and so on. So this lake is developed due to extension, some part of area subsided, and lakes developed on these lowlands. Okay. So this system is called inside intra-continent. This is continent Africa rift. With time, with continuous extension, this intracontinental rift will be developed, will be progressed to another stage of extension, what's called young ocean. It will develop to form what's called young ocean. Why we didn't say young ocean in this stage of rifting? Because still the floor of the rift here is continental crust, like in this diagram. Extension happened and some faults formed or fracture formed, but still the floor of the extensional regime is continental crust, so it's called intracontinental rift. When complete consuming of continental crust and new oceanic crust due to ascending of magma from a mantle developed here in the middle of the rift, so we are transferred from the initial rift stage to what's called ocean. So definition of ocean based on creation of new oceanic crust. Okay. Later on, due to pushing force of ascending magma and creation of oceanic crust, this push the continent away from each other, beside the extension stresses. So we have two forces here: the extension itself and also the pushing force of ascending magma, what's called spreading force. These two forces acting to increase the weights of ocean until the area beside the continent developed what's called passive margin. So at the continental side, at the continental margin, new substance occur due to thermal substance. What's called thermal substance? Because here in the middle of ocean, still the center of heat is here, sending heat. When this material moved away from the center of heat, source of heat in the middle of ocean, it will cool gradually. Cooling means shrinkage. This shrinkage will lead to vertical subsidence. This vertical substance was called thermal substance. So the substance in the passive margin is called thermal substance. Finally, we can conclude all of this as we have, due to extension, what's called intracontinental rifts, which develop to extension, young oceans, and then mature ocean. At the two sides of mature ocean, we have what's called passive margin. Okay. We can come back to this point. It's not necessary that all stage of extension achieved. We have three stages of extension: intracontinental rift in the initial stage, young ocean in the middle stage, the finally mature ocean with passive margin in the final stage. But sometimes extensions stop here in this process. So if the extension is not succeed to develop oceanic crust, it's called failed rift. Failed rift or inactive rift. The failed rift is called also Holacogene rift. So we have two types of rifts: active rift and successive rift, which developed literally with time to ocean. Inactive rift, Holacogene rift, is a failed rift, which are successful rift that cut into cratonic areas of continents at high angle to the continental margin are known as Holacogene rift. Okay. Still, we are talking here about with example from East African rift system. This is Red Sea and this is Gulf of Aden. It was like this Afro-Arabian plate, one plate, and with time the extension due to moving of Arabian plate towards Iran and the African plate towards west, a new rift system developed here between what's called Red Sea and Gulf of Aden. With extension progress, it's development of oceanic crust in the Gulf of Aden, and we started in Red Sea. So Red Sea is young ocean, Gulf of Aden is mature ocean, and so on. Okay. So with increasing the extension, the rift developed to transfer to oceans. Okay. We'll start with intracontinental rift, the initial rift stage. Rift is not almost area of extension, but is a rift system, okay, which is called belt of continental lithosphere that is currently undergoing extension, okay. Underwent extension in the past. If undergoing extension today, it's what's called active rift. It was under extension in the past. It means inactive rift. So in some time we can talk about Paleozoic rift. Paleozoic rift means that the rift was active during Paleozoic and ended at the end of Paleozoic, for example. Okay, so if we have example like this, we can call it as inactive. But today's recent activity of rift, like East African rift, like Atlantic Ocean, is active rifts. Today is subjected to extension today. Okay. Rifts forms when the crust is pulled apart by tectonic forces. We have two models of explanation of rifts. What's called active and passive model. The active models mean we have a source of pushing force from the inside Earth. What's called mantle force. That pushing part of crust up and away from each other. Okay, this is active source. The passive model mean we have far stresses which pulling these two plates away from each other and reactivate old inherited lineaments within the crust. So in active rifting, we have rising whole mantle material or plume in the atmospheric mantle, causing doming and adding tensile stress to the domal area. In the passive rifting, no, we have far-field stresses related to plate tectonics. Okay. This can be achieved by two models. What's called pure shear model and simple shear model. We have to say pure shear model meaning if we have maximum stress in this direction, okay, if we are going to apply stress in this direction, mean the crust will send in a vertical direction and it will extend in a lateral direction like this. This is a pure shear. So due to applying extensional stress in this way, stretching in this way, so thinning occur in this way. This is pure shear. In simple shear we have long shear zone, which mean this part of content or part of plates moving down this and this part moving up like this along this shear. In case of pure shear we have symmetrical rift system. In case of simple shear we have asymmetrical rift system. In case of pure shear we have the heat source in the middle of rift system. In case of simple shear we have heats not in the middle, in one part of rift. Okay. Later on, how the extension occur? Extension occur due to development of what's called normal faults. Normal faults. This normal faults rotates like this, so it's achieving type of extension due to rotation. We can explain it later on. So the first stage of extension achieved by development of fracture in the upper part of the crust, and this can be successfully followed by thermal suffusion due to shrinkage of heat here or ascending mantle here will cause substance later on in the late stage of rift. This is not the case of impure simple shear, because the first stage is achieved by normal faulting, but the last stage we have heat here in the center of the rift system, so we will not have what's called thermal substance in the later stage. Okay. But actually, in most rifts in the world, we have asymmetrical geometry, not symmetrical geometry. So in most cases, we have this form of extension, asymmetrical shape of rifts, not symmetrical. So simple shear models have the advantages of reality, explaining the symmetry of many rifts. One side of rift called the roll plates, one side of rift called lower plate and undergoes extension stretching, while the other side called the upper plate undergoes less stretching. Okay, so this is the upper plate is going under extension, and this is lower plate, nothing of extension. So this is the case of most rifts in the world. We have asymmetrical rifts. But some authors, some scientists in the world make a combination between pure shear and simple shear model representing the actual geometry of rifts. So most of rifts can develop due to pure and simple shear in the same time. Okay. We have what's called core complex, metamorphic core complex. In the simple shear model, with time, continuous extension meaning thinning of crust until the mantle ascending up like this, until the mantle exposed the surface, exposure of myelinites to the surface. This is what's called some metamorphic core of, due to extension can form core. It's not necessary to understand this because it's not a matter of interesting today for you in this level of education, but maybe later to understand what's called metamorphic core complex. But we have to know with continuous extension, some parts of deep inside the crust or even mantle can be exposed due to continuous stretching and thinning of the crust. Okay. How the rift system develop? Rift system begin as a series of unconnected rift segments. Lead extension. Then each containing a set of normal faults. Each rift segments containing a set of normal faults. Due to continuous extension, each segments extend along its strike and its dip until it will be linked with another segment and so on. Okay, this case also in the normal faults. Between rift segments, we have what's called accommodation zone. If we see here, for example, in Egypt, is the Gulf of Suez is a intercontinental rift system spread between Sinai Plate and Eastern Desert Plate. Gulf of Suez is divided in three rift segments: the northern rift segment, central rift segments, and southern rift segments. Each rift segments have a lot of normal faults like this, extensional faults. All of these faults was small separated faults. With time, it's linked with another segment here and another segment here until we have well-developed rift system due to linkage of three segments of rift. This through what's called accommodation zone. So you have accommodation zone here is a Morgan accommodation zone. You have another accommodation zone here is the Savarana accommodation zone. Okay. Cross section here explain what is the geometry of rift. It's a symmetrical rift. Okay, the main faults bounding this from this side, and all of strata dip away rotated in this way against the main bounding fault here. In the middle part we have cross section, but with reverse polarity. The main fault become in the eastern side, and all of the bedding dips in the opposite direction like here. The last section is here. We have the main fault towards west and all strata tilted beds dipping towards west. That's case example of how two rift segments link together by what's called accommodation zone. Accommodation or transfer zone is a sharp or diffuse boundary separating between rift segments with faults of opposite dip. Here faulting is dipping this way and fault is dipping this way, so the accommodation zone is a zone of diffuse deformations which separating between two segments of rift with opposite rift fault dip. Usually this zone characterized by oblique slip movements because it will be accommodate movement between this segment to this segment. So we have oblique يعني normal with extension, normal with extension. So extension maybe towards this and towards this part towards this and this part towards this part, and we have oblique movement like this. Okay. Usually it's developed at termination of faults. This fault is have maximum through in this point and decrease towards this point. This fault have maximum displacement here and decrease this point. So this area is usually higher within the rift. They can be presented at a variety of scales. Maybe scale from fault scale, fault to fault transfer to zone to zone. Okay. Rift geometry and accommodation zone influence sedimentations, pattern, and lithology. This is a case of this is rift segment and this rift segment. In between we have accommodation zone. It's a high area separated between two rift systems. If we see here, the maximum displacement is here, the fault, decreasing from the center of the fault until it reaches zero as accommodation zone. Also this fault maximum displacement here and decrease to be minimum or zero as accommodation zone. So the accommodation zone is a higher rise of the fused structures, okay, separated between the rift segments. Developed stage of rifts, we have here fracture pattern in the stage developed due to stretching, some rotation of bedding to achieve thinning of the crust, and the filling of the rift later on post-rift subsidence and sedimentation due to what's called internal subsidence. The typical geometry of half graben or half rift system. Here in this section we can divide sediments of rift into three sequences. This in orange is the pre-rift sequence, and this in green is the thin rift which developed during the rift extension, and this one is white is the post-rift sequence. So we have three sediments sequence. Also here we can see that usually pre-rift sequence is have this constant thickness in upstream and downstream of faults. Thickness is constant, no change of thickness. If we see as the orange bit here with the same thickness, not a change. but green one, light green, is have geometry what's called wedge shape. This wedge shape with maximum thickness besides faults and degrees away from fault like this. Here we have, this is section is pre-rift section, but this section is post thin rift section. Because why? Each fault have what's called a thin extension segment. Look at this. It's look a wedge shape. Maximum here, decrease away from the fault like this. In general, we have thin rift sequence with starting from this yellow line until this orange line. This sequence increasing the faults near the fault and decrease away from the main fault. And this part is post-rift use. So we have pre-rift, thin rift, and post-rift sequence. Here we have also pre-rift sequence, thin rift sequence here with a wedge shape geometry, and post-rift sequence with the same geometry. But this is another rift system. Okay. We have some basic terminology of rift system that we can say. The main bounding fault of the rift is maybe lithric or planar fault. But this fault we can see it as synthetic fault. Any fault in opposite direction to it, it's called antisthetic fault. So the main boundary faults, like this with the biggest straw and the bounding the rift is called main faults. And any faults take the same depth direction of the main fault is a synthetic fault. Any fault is opposite to the main fault is antisthetic fault. If the fault is curved fault, meaning the depth of the fault decreases downward until it reaches zero with detachment level or detachment fault, it's called lithric fault. So we have planar fault like this with this almost continuous depth from up to down, and we have a lithric fault, which meaning decreasing the depth angle until level of detachment 0 with 0 angle. Again, the main bounding fault is the main faults. Any fault, small faults with the same depth of main fault is synthetic. Any faults with opposite depth of the main fault is antisthetic. If the fault depth with the same angle is planar. If the fault depth as a curved fault is lithric fault. The lower part with zero angle of depth of lithric fault is called detachment fault. This is a physical model with sand body showing the geometry of rift system. We have a comparison between planar fault and lithric fault. Planar fault meaning fault whose depth remains constant with depth is a planar fault. Okay, lithric fault, depth curved, fault curved until the fault reach what's called detachment level. Okay. Pre-rift segments here is with no rotation. He's a big rotation, but reverse rotation against the fault itself. In planar faults, extension achieved due to rotation. If we have this is the initial length before faulting and movement along faults with angle 60, until rotation the length extended but the vertical thickness decreased. So here is stretching achieved due to stretching, okay, and stretching achieved by rotation along fault from 60 to 30. Okay, so from this figure we have to understand how is the stretching achieved due to faulting, this initial faults, but this fault we have to rotate from 60 degree to 30 degree. Due to rotation of faults, okay, this length, initial length, increased to be L plus extension. What happened E? But due to the stretching, this vertical thickness decreased to be less than T naught. Okay. Due to extension, here some basins developed, or space developed. This received what's called thin rift sediments. And after consisting of the faults, stopping of these faults, post-rift sequence developed with flow line. We have pre-rift sequence, thin rift sequence, and post-rift sequence. Okay. In electric faults, extension have what's called rollover anticlines. Due to extension at detachment like this, we have a space problem here. So this part of moved plates or moved clock will be pending to fill this space, develop what's called rollover anticline. In some cases, with some geometry of not electric like this, maybe two electric linked, which is the development of rollover anticline will be like this more big complex. It's not matter of interest for you. This is the geometry of rollover anticline. Sometimes this space problem may be solved by what's called compensate faults, like fault here to make this part moving down to fill the space here. Okay. This is what's called seismic section. Seismic section is geophysical data due to sounding. It's not interest in not matter of discussion here in structure, but this show the geometry of extension faults. Okay, we finished today. We see you in the next lecture of extension, inshallah. Soon I will prepare it for you and see you. Any question you can add it in Blackboard for me and we'll answer you.